What I'd like to do is walk through an explanation and examples of snapshot and history graphs. These are two ways to analyze some one-dimensional wave motion. Very often, students find this to be a bit of a struggle, so I wanted to walk through it step by step. We're starting off with a snapshot graph. And what we see here is we have a wave with, well, we've got some medium. Let's consider it could be a rope or a string. And it's going to have a slightly asymmetric shape. So we see that there's going to be a steep angle on one side. So we can do a little highlighter here and say, well, we want to think about the fact that we've got a steep angle here, and then on the other side we have a more gradual slope. And so let's pay attention as we analyze this motion, how that is going to play out. Okay, so with a snapshot graph, we're really looking at what is the displacement across X. So maybe just think of this as a photo of a string that has some wave pulse moving through it. We're told that we have some velocity of 1 meter per second towards the right. Great. So we can ask ourselves, well, what is it going to do next? And we can say, well, this particular image is at t is equal to 0 seconds. In the snapshot graph, we're keeping time constant. So this is a plot of t is equal to 0. What would happen at t is equal to 1 second? So we can draw another snapshot graph, and we're going to overlay it right on top. And before we do that, I'm going to make sure this is really clearly labeled so that blue is t is equal to 0 seconds. Okay, let's move on to the next second. We know that this wave pulse is moving towards the right at 1 meter per second. Okay, we also know that if we want to relate a velocity and time into a distance to figure out where exactly that wave pulse will be, we have an equation. We can use v is equal to d over t. And we can rearrange to get something more directly useful and say, well, d is going to be equal to v times t. So, the longer the distance, will either take a faster speed or more time. Okay, so maybe I'll just pick that up and I'll move that off to the side for reference. Okay, knowing that if we have t is equal to, let's say, 1 second, where is that going to put the wave? Well, at 1 meter per second, we'll have a wave that moves 1 meter. And so let's just pick out a point. And this is really the strategy I recommend. Think about some key points here. This entire waveform can really be inferred from the location of these 3 key points. So let's pick them one at a time. That first point where we go from a displacement of 0 to the start of that sharp incline will move 1 full meter forwards. So we can say, well, that's where it's going to be. So this point is going to move up that much. Okay, then we can look at that second point where we have the peak. Where is that going to be in 1 second? And that's going to be right about here. So we're again moving up some delta x of 1 meter. So our delta x is equal to that 1 meter, and that's because our speed is 1 meter per second and our delta t is 1 second. Okay, and then finally this last point will be located 1 meter beyond here, and that's going to be here. Okay, And so now if I want, I can just draw the whole wave pattern. Okay, so that's where we're going to be at t is equal to 1 second. And we could do this a few more times and map out exactly how this whole waveform is going to move. Let's pick maybe green, and we'll do this again for t is equal to 2 seconds. So again, 1 more second will pass, and so we'll have another delta x of 1 more meter from our t is equal to 1 second. Or we could consider from the original position in 2 seconds, we move a delta x of 2 meters. Okay, so we'll have a dot there, and then we'll have our peak will be 1 meter further, and then our end will be over here. Okay, and we'll just fill in the gaps. It's a bit crowded, but we'll zoom in and we'll put a little t is equal to 2 seconds in green. Okay. We're going to do 2 more, and you're going to understand why in a moment. Okay, so let's go back to black. We could do some sort of, we'll go kind of a purple. Okay, so let's do t is equal to 3 seconds. So again, we move 1 meter. Do this a little bit quicker this time. There and there. I think we're probably getting a sense of this pattern. Here we go, and here we go. And we're going to zoom in again. T is equal to 3 seconds. And zoom back out. And we'll do one final one in brown. And that's going to be t is equal to 4 seconds. And so we're going to have here, we're going to have our peak here, and the end of our wave pulse over there. And we're going to connect all this together. And pretty close. That's pretty good. Okay. Fill that in just a little bit. Okay, so now we have a sequence of snapshot graphs, and they're showing that the pulse is moving from left to right in time at that 1 meter per second speed. Overall, we can kind of verify, well, we've got the same pattern, and that whole waveform. In fact, I'm going to make a note of this. It'll be useful in a moment. I'm just going to make a note, and I'm going to want some dotted lines. I just want to note that the whole waveform here that we're thinking about, this wave pulse pattern, is itself, how long is that? That's 1, 2, 3, 4 meters. So the whole kind of pattern here, delta x is 4 meters. That's going to be useful in a moment. Okay, so here's our series of snapshot graphs showing evolution in time. And so that brings us to the next big topic, which is what if we don't keep time constant and look at the displacement over x, but instead look at keeping a location constant, and that's our history graph. So our history graph is really picking a single point and asking what's happening at that location over time. And so I've drawn a little figure here right at x is equal to 6. And so we can ask, for example, over time, what's happening at that location? And that will be our history graph. Okay. Well, first let's look at this conceptually. What's going to happen for t is equal to 0? At t is equal to 0, there is no displacement. Nothing's happening, but if we were observing, we would probably be terrified by the sight of this enormous wave approaching us, knowing something is on its way. noting the relative difference between the height of the person and the wave. Okay, so how long until that wave hits us? Well, it's 1 meter away, traveling at 1 meter per second, so we have 1 second. So in 1 second, we're going to start to have that wave. And the first thing that's going to happen is we're going to see an increase in the displacement up this gradual incline, up into some peak, which is 2 meters of displacement. And the second thing, if we're breaking this down into kind of phases, the second thing that happens is we're going to then have a decrease in our displacement that occurs much more rapidly as we go down this side of the wave pulse. And then we return to 0. So conceptually, that's what's happening step by step. Let's now plot that out. So we're going to go down to our history graph. Notice that our history graph has, again, displacement on the y-axis, but this time we're looking at the evolution in time of some specific location. In our case, x is equal to 6 meters. How do we begin? Well, I'm going to start by just choosing a color here, and we're going to go with red. What I want to start with is what's happening at t is equal to 0. Well, let's go back up here. Blue is 0 in this one, so we'll stick with blue for this. Okay, so at t is equal to 0, what's happening at x is equal to 6? Well, nothing really is happening. So we're still at a displacement of 0. So at time is equal to 0, we are at 0. Okay, what about time is equal to 1? What's happening at 6? Well, let's look at our orange color, and we see still nothing's happening. Okay, the wave has arrived, and we're about to be changing our displacement, but we're not there quite yet. So here we go. Orange dot, still at 0, but we know that we are about to change. Okay, what about the next second? That's green. So we're going to go to green, and we have, okay, now something's definitely happening, because at x is equal to 6, we are up here. And that looks to be just a little bit less than 1. Okay, so we'll go over here, and we'll try to approximately say, I don't know, there. Okay, one more second, we went to purple, and at 3 seconds, where are we? At x is equal to 6. Looks like 1.5-ish, somewhere in there. Okay, so we're going up, and so we're going to go somewhere around here, not quite sure. And then lastly, let's do this when I didn't denote that brown was 1 second later. So that is t is equal to 4 seconds. And at t is equal to 4 seconds, we are at that 2 meter maximum displacement. Okay, so we're coming back here, and we've got 2 meters. All right, so then what happens? Well, we've only drawn this out, and so of course our x is going to be up here at the dot. We've only drawn this out for the first 4 seconds. Now we can maybe take a different approach to do the rest. Well, we know that 1 second later, we're going to be back down to 0, because this whole section of the wave, well, that takes 1 second to pass through, because we've got a delta x here of 1 meter and a velocity of 1 meter per second. So that part of the waveform is going to take 1 second, and so we're going to be bringing it back down to 0. Okay, so now we can fill out this whole wave passing through this x is equal to 6 meters. and get a plot. And we'll do that in red. Maybe I'll increase this a little bit. Go a little bit bigger. Okay. And so we're going to go all the way up to 2 and then back down to 0 and onwards. Because as time moves beyond that point, the wave pulses move through x is equal to 6 and we're back to 0. So that then is our history graph. Notice the relationship between these two graphs. In this case, we have essentially the mirror image. Initially, in the snapshot case, we had the short, steep side and then the longer side. And then in this case, they are flipped. And that's because we're looking at the point of view of one location that experiences that slow, gradual increase first and then the steep decline. So that's our snapshot and history graph. Okay, is that everything we need to know? Well, yes, but there are a couple of things that sometimes get students a little more confused. So I'd like to, if you want to dive into those two examples, go and look at two changes to this question. Okay, let's start again from the same snapshot graph. But in this case, instead, we're going to be looking at a case where the history graph asks us for the location kept constant at x is equal to 150 meters. Let's draw the history graph at 150 meters. Okay, I don't know why we would do that, but let's say that we are interested in some point that is far away. Well, okay, how do we do that? First of all, let's pick a scale for our time that has some connection to when it's going to actually reach that far into the distance. So, okay, we have a delta x here. Let's consider, some sort of delta x. We want to know what's going to happen at 150 meters. And how big is our wave pulse? Well, our wave pulse, as we drew previously, well, this whole thing is a delta x of, this is about, this is 5, this is 1, so 4 meters. Okay, so we want to give ourselves a little bit of room. So let's give ourselves an extra meter, and so we'll say minus 5 meters. And it'll become obvious where I'm going with this. I'm trying to figure out whereabouts I should start my graph. And I'm going to start it at about 145 meters. Okay. Now, if my velocity is 1 meter per second, then at what time do I reach 145 meters? Well, 145 seconds. So I'm going to start here at 145, 146, and onwards. Just give me a moment. Okay, so now I have a reasonable scale for the time period when this pulse will actually arrive at the designated location of 150 meters. Okay, so how do I work out exactly which one connects to which? Okay, well, let's consider this location here, the very leading edge of this wave pulse. This at t is equal to 0 seconds, this is located at x is equal to 5 meters. And so from that, we can say we already know that at 145 seconds, this is going to be located at our 150 meters. So that can be our starting point. So 145 will be our first point. Then we can ask, okay, well, how long will it take for this point to arrive at 150 meters? Well, that's starting at 2, and so we can look to say, well, how long after this point arrives will it take for this point to arrive? Well, that distance here, this part of the pattern, well, this is a delta x that's equal to 3 meters. And so how long does it take for the wave to move 3 meters? Well, it will take 3 seconds. So we expect that 3 seconds later we'll reach that maximum. So we'll go from 145 up 1, 2, 3, and we can map out that it will reach a maximum displacement at 148. And lastly, we can chart out what's going to be the time when this particular part of the wave reaches that 150 meters. And that's going to be, well, how much longer do we have to wait? Well, this is a delta x of 1 meter, and so it'll be 1 second later. So we'll go up to 149. And so here now we can plot out what the history graph looks like for x is equal to 150 meters. And there we go. Notice that this looks basically identical to our previous history graph, that history of x is equal to 6 meters. And of course, every point along this rope or string or whatever is going to have this same pattern pass through it. It's simply a matter of when. So the difference here is looking at the speed of that wave, the distance away, and figuring out at what time that wave is going to reach it. And really, once you get that first anchor point, which was this here for us, these 3 anchor points, you can just map this out. You can pick any of these, and really it's probably easiest to start with the first one that arrives or the last one that arrives, but any of them really work. You just pick one, that becomes your anchor, and then as we did here, we said, well, this one arrives, and then after that it takes 3 seconds, and then after that it takes 1 second, and we have the whole wave. But you could do any of them. So that's dealing with a location that is, not as trivial. One last thing, and this is going to be a little bit more challenging, but we're going to follow the exact same logic. And that's going to be the case where the velocity is not going to be 1 meter per second. We're actually going to have to think very carefully about how the velocity affects our history graph. Notice that in both these other examples, we had a fairly trivial mapping. It was just going to be flipped. It's going to be a bit more complicated when we start here with our snapshot graph, but instead have a velocity that isn't 1. In this case, we'll use 2 meters per second. Okay, so again, though, we're going to use a history graph at our reference of x is equal to 6 meters. So we're going to be looking at the point of view of our little character here. Okay, but now we're going to use a history graph at 6 meters, but now we have this velocity of 2 meters per second. Well, okay, how do we handle this? We're going to do the same thing, but we're going to have to be careful. Let's think about what we were doing before really carefully. The first thing we can consider is at t is equal to 0. Okay, we know the trivial one. So t is equal to 0, displacement is 0. We're good there. Now, however, things change. When will this point in the wave arrive? So it's moving towards you at 2 meters per second. Well, in this case, at 2 meters per second, it will travel this distance, which is 1 meter. It's going to take a delta t of only 0.5 seconds, or half a second. So when we do our history graph, we're going to go to just half a second, and that's going to be the point at which that first wave arrives. Now we can ask how much longer for the peak to arrive. Well, I think what I'll do is I'm going to look at this full distance here from, okay, just make this level. Okay, good. So I'm just going to look at this now. So from t is equal to 0 to when I get to this peak, this is going to be a delta x of 4 meters. So we have a delta x of 4 meters. We have a velocity of 2 meters per second. And so how long is that going to take to arrive? That's going to take 2 seconds. To arrive at x is equal to 6 meters. Okay, so that means at 2 seconds, we're going to have a displacement of that 2 meters. And then finally, we can look at this last anchor point for this whole form and say, well, when will that part arrive? And you could do this a couple of ways. You could do it straight from our reference point all the way out there. I'm going to think about it as just tacking on an extra 1 meter. So our delta x for that part is going to be 1 meter. How long at 2 meters per second will that take? Well, it's the same as what happened here. It's going to be half a second. And so half a second later, that last point will arrive. And so note what happens in this case. Let's draw out this history graph. And after that, 0. Well, this is a little bit different. It's very similar, but a little bit different. It all happens more quickly because that velocity is going to be larger. And that makes the history graph compressed. It's the same basic shape. It's still inverted, right? Because here, if we highlight, just to remember, this is our gradual slope, and this is our steep slope. And then we go down to our history graph. We still have the steep slope, and we still have our gentle slope. So all of that still happens just as before. But in this case, this is all happening in a smaller period of time. If we look at the entire time for this to pass through, we're going from 2.5 seconds to half a second. So this whole delta t is taking 2 seconds. For a 4 meter long wave to pass x is equal to 6 meters at a velocity of 2 meters per second. Okay, So that's our example where we have a snapshot to history graph, but in the case where the velocity is going to be some number other than 1. So hopefully these examples give more of an intuition for how snapshot and history graphs work.